Okay, so in this section, we're going to be talking about tangent lines and derivatives. So even though everything we've seen so far with limits is, of course, calculus concepts, this is when we really get into some nice hardcore calculus concepts. So starting off here, we're going to start off with a couple definitions. We'll first talk about what a tangent line is, and then we'll talk about the tangent line as a limit of secant lines. So starting off here with what a tangent line is, you might have remembered this from like a geometry class. A tangent line on a curve is going to be a line that touches the curve at one point. Technically, it could intersect the curve at other points as well, but we're only interested at this one point. It touches the curve at one point, and it indicates the direction of the curve at that point as well. So tangent literally comes from the Latin word for touching. So it's touching the curve at this one point, and it indicates the direction of the curve at that point. So if we had another point over here on the left, it looks like the curve is increasing over here on the left. So the tangent line might look something like this at that point. It's touching it directly at the point, and it indicates the direction of the curve at that point. So let's go ahead and see another example, because we don't always have to use circles. Let's take a look at this part right here. So we have this curve, this blue curve right here, and then we have these 1, 2, 3, 4, 5 different points. And it looks like, let's take a look at the points individually. Point P1. Point P1, that line is a tangent line because it's not only touching it at that point, but it looks like it's going in the same direction of the curve at that point. Let's look at P2. So the line going through the curve at P2, it's cutting through the point at that, it's cutting through the curve at that point, but it doesn't look like it has the same direction. So this line would not be a tangent line. For the point P3, this does look like a tangent line cutting through P3 because it's cutting through the point. It looks like it has the same direction. For P4, P4 almost looks like that is correct. It's touching the curve at the point, and it looks like it's very close, but the actual tangent line would probably be a little bit less steep. It would probably look maybe more so something like that right there. And then lastly, P5 does not look like a tangent line because it does not look like it has the same direction of the curve at that point. So a lot of the stuff that we're going to be doing right now, just like we kind of saw with limits, has to do with like a lot of motion. And it might help. I'm going to give this little button a click right here. It might help when you look at videos or GIFs when we're talking about these calculus techniques. So clicking this to see how a tangent line moves along a curve, that would look something like this. So notice we have this black curve, maybe a polynomial curve here, and the red line is the tangent line, and it's moving along the curve from left to right. So notice that it's kind of going along with the direction of the curve. It's increasing when the curve is increasing, decreasing when the curve is decreasing, and it's horizontal when the curve has a relative max or a relative minima. So a lot of these calculus techniques that we're going to be reviewing, it's really going to be helpful to think in terms of motion. Actually think about it moving along the curve. Okay, so now for the next little definition here. Let's see what is a secant line. We already know a tangent line touches the curve at one point of interest, and it has the same direction of the curve at that point. Now let's see what a secant line represents. So the simplest definition of a secant line, and all it actually is going to be a line connecting 2 points on the curve. So secant comes from the Latin word for cutting through. So a secant line is just a line, essentially cutting through 2 specific points of interest on a curve. So what we're going to do here, let's go ahead and take this. We're going to relate a secant line to a tangent line and how it relates with these calculus techniques. Let's say we have a function, And let's say the function looks something like this. And then let's say we have 2 points of interest. Let's say we have this point right here, which we're going to call R. And before we want to actually, before we talk about the second point that we're going to use in a second, let's say we want to figure out what is the slope of the curve at this point R. So when we think about finding the slope of a curve, we probably think slope formula, right? You cannot use the slope formula for a singular point. That doesn't work because in order to use the slope formula, you need 2 separate points. So if we want to figure out the slope of the curve at R, which was going to be the slope of the tangent line at R, what we actually have to first do is discuss or introduce a second point. Let's just call this point S. And between these 2 points, we're going to create a line connecting them, and this is going to be called the secant line. So we can easily determine the slope of this secant line, right? So let's go ahead and say that the notation is going to look confusing for a second, but hopefully it makes sense when we see the formula we're about to use. Let's say that the R point has an x coordinate of A, and then the S point has an x coordinate of any x value. And I'll mention why we're using x for the x coordinate of S in a second here. So we can easily determine the slope of this secant line by using the slope formula between 2 points, right? We know the slope formula between 2 points is y2 minus y1 over x2 minus x1. If we are using these 2 x coordinates, then this would be the slope between R and S, right? So y2 minus y1 over x2 minus x1 would end up being f of x minus f of A divided by x minus A. So that's just the slope formula using these points A and x for our x coordinates for these 2 points. So other than the weird notation that we're using, the question is, how does this secant line, how does the slope of this secant line relate to the slope of the tangent line at R? How can we use this secant line to actually help us determine the slope of this tangent line at R? So just like we mentioned on the previous page, we're actually going to use this concept of motion. We're going to fix point R because that's the point we want to know the tangent line at, the slope of the tangent line at. We're going to keep R the same, and then we're going to take point S, and we're going to move point S closer and closer to point R. So that's the reasoning why I'm keeping this as an x, because it's still going to be a variable. It's going to be any x value, and it's going to be getting closer and closer to point A. So the idea for this, before I show a little video, because it's going to make more sense with a nice little video or a GIF demonstration, the idea for this is that as this point gets closer and closer to point R, or think of it as x gets closer and closer to A, the slope of the secant line is going to get closer and closer to the slope of the tangent line at point R. So let's go ahead and see a little demonstration of this by clicking this little link right here. Okay, so we have this curve. Of course, it's the blue curve. So that black point on the left, that's the fixed point. That's going to be the point that we're interested in determining the slope of the tangent line at. So the point on the right that's moving, that would be that point S. We're moving that point closer and closer to point R on the left. And notice that there's a secant line cutting through them the entire way. So in general, as S moves closer and closer to point R, that slope of that secant line is getting closer and closer to the slope of the tangent line until it's directly on top of it when it becomes the tangent line itself. So in general, as the x value for the point on the right gets closer to the x value to the point on the left, the secant line slope is becoming closer and closer to the slope of the tangent line for the point on the left. So that brings us back to this first main definition here, which is going to tell us the slope of the tangent line at any point on the graph. So remember, we can't just find the slope of a singular point using the slope formula because it would end up giving us 0 over 0. The slope formula needs two separate points, but what we can do is introduce these calculus techniques with limits and use this weirdly looking slope formula to actually find the slope of the tangent line, which means we find the slope at a singular point on the curve. This is also called the instantaneous rate of change of a function at a certain point. So we have the slope of the tangent line is going to be the limit as x approaches a of f of x minus f of a over x minus a. So we already discussed the reasoning for this, because as x approaches a, taking a look at this graph right up here, as x moves closer and closer to a, the secant line is going to become closer and closer to that tangent line, and that's exactly what this formula represents. So before we see an example actually using that little formula, let's take this one step further with definitions. And this next definition is going to be one of like the pillars other than limits. Limits is kind of like the main pillar of calculus. Derivatives is going to be kind of like a step up from limits. So taking us to what is a derivative of a function. And then we'll come back to that formula we talked about in 1 second. So we already know what f of x represents. F of x in general just tells us the y value of a function, right? F of x is the y value, the function value, the distance away from the x-axis, or the height of a function. What we're going to do now is going to create another function from f of x, and it's going to be called the derivative function. So we're going to denote the derivative function with this little apostrophe, and it's going to be called the derivative of f of x, or you can call it f prime. They both mean the same thing. So what this is going to represent, when we evaluate the derivative at a certain value, this is going to represent the slope of the curve, or the slope of the tangent line, or the instantaneous rate of change at that point. So when we think about the derivative as a function, which we will in a little bit, you think about the derivative as telling you the slope of the function at a certain point. So we can rewrite that definition we learned on the previous page. This is the same definition we learned on the previous page. Right? This represents the slope of the tangent line at any point A. So f, now with new notation, f prime of a represents the derivative of the function at an x value a, which represents the slope of the tangent line at x equals a, or the instantaneous rate of change at x equals a. So let's see an example, and then we'll talk about like what it represents graphically after we get a numerical answer. So let's say we want to find f prime of 4, where f of x equals the square root of x. So it's going to be a little bit confusing because there's going to be several different ways we could do some of these questions. It should make sense. Hopefully, we'll bring it all together at the end. So we're going to go ahead and just use that definition we talked about that was written above. F prime of a equals limit of f as x approaches a of f of x minus f of a divided by x minus a. So notation is very, very important. Make sure you have everything kind of written the way I have it written. So we want to find f prime of 4. Before we even find this, just think about what it means. I'm going to write down what it means when we actually get a number. Just think about what it means. F prime of 4 means we're finding the slope of the tangent line at x equals 4, or think of it as finding the instantaneous rate of change of the function at x equals 4, or just think of it as finding the slope of the function at x equals 4. So let's go ahead and plug in a 4 into all of these a's. So this is going to be the limit. We're finding the limit as x approaches 4 of f of x minus f of 4 over x minus 4. So these always look trickier right from the beginning because you have to plug everything in correctly. We just substituted in a 4 into all of the a values. That's the value that we would think of being held constant here. And before we can evaluate this limit, we just need to plug in 2 more things. We need to plug in f of x and f of 4. Everything else seems good to go, right? Limit as x approaches 4, and then x minus 4 in the denominator. Nothing really to simplify there. What we need to do is simplify or rewrite f of x as the square root of x, because that's, of course, what the square root of x, that's what f of x is, the square root of x. And then we can rewrite this f of 4 by just evaluating f of 4. So f of 4 is the square root of 4, which is 2. So f of 4 is just 2. So all we did so far was use our formula right from the beginning that was given to us here, and then we plugged in the 4 into all of the a's, and then we had to replace f of x with the square root of x, replace f of 4 by evaluating f of 4 first. So now we finally got to the point where we can evaluate this limit just like we've been doing in the past couple sections. We want to evaluate the limit as x approaches 4 of the square root of x minus 2 over x minus 4. So remember, we should usually try direct substitution first. Spoiler alert, direct substitution's never going to work right away for these questions. So you can try it if you want. It's not going to work. We need to rewrite this expression, this function. And it looks like technically you could use factoring, but usually if we see the square root, we should be thinking about rationalizing because of the square root. So we multiply the numerator and denominator by the conjugate. And that's the conjugate of the numerator, so square root of x plus 2. And remember, when you multiply conjugates, you get the first one squared minus the second one squared. So that's going to be square root of x squared is just x, minus 2 squared is 4. So this is what this simplifies to in the numerator. And then the denominator, you just always rewrite the denominator is exactly how you see it. X minus 4 times the square root of x plus 2. And then just like we saw in the past few sections, those will cancel, those factors of x minus 4. And all we're left with is 1, because the factor is canceled, over the square root of x plus 2. Now we can apply direct substitution. 1 over the square root of 4 plus 2. 1 over 2 plus 2. That gives us 1 over 4. Okay, so now the question becomes, what the heck does this represent? So our function here was the square root of x. I'm going to do a quick little diagram here on the right. So we have the square root of x looks just something like this. And the point of interest here was x equals 4. So what we just found, we found that f prime of 4, the derivative evaluated at 4, is 1/4. So what that actually represents is the slope of that tangent line at x equals 4. So that seems reasonable, right? Just by this rough sketch, it looks like the slope of that line, sure, slope of the line looks like 1/4. And it also represents the instantaneous rate of change of the function at that point. Or you can think about the instantaneous rate of change is just the slope of the function at that singular point. Okay. Let's find the following, where f of x equals x squared. So we want to find f prime of a. So let's go ahead and write down our formula. F prime of a equals the limit as x approaches a of f of x minus f of a over x minus a. And always, even though you can probably run through a lot of questions without knowing what it represents, I'm going to say it every single time. F prime of a, this is the derivative of the function evaluated at x equals a. It's going to tell us the slope of the tangent line at any x value a. So let's go ahead and plug some stuff in. It's going to look a little bit different, maybe a little bit trickier, just because we don't have an actual value, we just have a. But let's go ahead and see what happens. So we end up having, in the denominator, it stays the same, right? X approaches a, x minus a, there's nothing to substitute in. Those stay the same. The numerator is the part that we always can change. F of x is x squared, and then f of a is a squared. So f of x is just x squared, and then f of a is plugging in an a, which is a squared. So what we have right now is to evaluate this limit with no numbers in here, just some letters. So the important thing to remember is that you can always try direct substitution. It's not going to work for these questions right away. And we have to remember our techniques. Remember, we just did rationalizing a second ago. This one's going to be factoring. The numerator here, even though it's kind of tricky, the numerator is actually difference of squares. X squared minus a squared, that factors to x plus a times x minus a, right? Even though it looks tricky, it's just difference of squares, like x squared minus 4 factors to x plus 2 times x minus 2. Same exact thing, just looks a little bit trickier. And we can go ahead and cancel off x minus a over x minus a. And we end up getting limit as x approaches a of x plus a. Now we can apply direct substitution. As x approaches a, we plug in the a into x, and we end up getting a plus a, which is, of course, 2a. So once again, probably looks weird when we have just a letter here. What does this represent? F prime of a equals 2a means the derivative evaluated at any x value a is 2 times a. So we can actually use, this is kind of like a generalized derivative, which means we can actually use this to find the derivative of this function at any x value that we want. So for example, if we have finding f prime of 2, we now have two different ways to do this. So this is going to be using that same formula. Let's kind of set it up the same way. So just our generic formula, f prime of a equals limit of x approaches a, f of x minus f of a over x minus a. We want to find f prime of negative 2. So we're going to go ahead and replace all of these a's with a negative 2. So we made it limit as x approaches negative 2, f of x minus f of negative 2. And then instead of writing x minus negative 2 in the denominator, I just changed that to x plus 2. Okay, so we have one more thing to do before we start actually evaluating this limit. As usual, we need to just rewrite f of x and f of negative 2. Everything else is good to go. So f of x for this question was x squared. So replace the f of x with x squared. And then f of negative 2 is just negative 2 squared. So f of negative 2, negative 2 squared, plug it in the function, which is 4. And we end up getting limit as x approaches negative 2 of x squared minus 4 over x plus 2. Once again, all we have to do now is evaluate this limit. And if you try direct substitution, it's not going to work. We get 0 over 0. So we're going to have to do something. We're going to have to rewrite it. And hopefully this one's a little bit more obvious that this is going to be factoring. The numerator factors to difference of squares, x plus 2 times x minus 2. Denominator is x plus 2, which is perfect because x plus 2 divided by x plus 2 will cancel. We have limit as x approaches negative 2 of x minus 2. Now we can do direct substitution, plug in our negative 2 into the x, negative 2 minus 2, and we end up getting negative 4. So we just found out that f prime of negative 2 equals negative 4. So like I said at the beginning of this question, and you might have realized, we actually could have done this another way. We already had this generalized statement for the derivative. F prime of a equals 2 times a. So we really could have just used that and said f prime of negative 2 equals 2 times negative 2, which is negative 4, and then we would be done. So realistically, if you already did this first part like we did up here, you do not need to run through and do this all again. You can just use this already generalized equation for the derivative, plug in your value, and then you are done. So basically just did a lot of extra work there. Let's see what this looks like graphically. Okay, so this was our function, f of x equals x squared, something like this parabola, crappily drawn parabola I have here. And we wanted to find f prime of negative 2. So the point is right here on the curve. And what we just found, f prime of negative 2 equals negative 4, we just found the slope of this tangent line, which sure, negative 4 seems reasonable for what I just drew in here. We just found the slope of this tangent line, which is negative 4, or the instantaneous rate of change, or the slope at this singular point on the function. Okay, we can use this technique to actually go one step further, and we can actually find the equation of a tangent line at a certain point on a curve. So anytime you're trying to find the equation of a line, almost always I should say, you're going to use the point slope form for the equation of a line. So the point slope form for the equation of a line is y minus y1 equals m times x minus x1. And anytime you're trying to create the equation of a line using the point slope form, you need exactly what it says. You need a point, which is the x1, y1, and you need the slope at of the line, which is m. So we're actually told that the graph we're using is f of x equals x squared, and the point is 1, 1. So we already know x1 is 1, y1 is also 1. If you were not given y1, you might just be given x. You would have to find the y coordinate by plugging in the x coordinate into the function. So we already have x1, we have y1. The question is, what the heck is m? So in order to find the m value, we have to use our definition. The m value, the slope of the tangent line, is going to be the derivative of the function evaluated at the x coordinate of 1. So using the formula from before, f prime of a equals limit as x approaches a of f of x minus f of a over x minus a. So I just went a little bit quicker and plugged in the a value of 1 right away. And now we can go ahead and plug in f of x. F of x here is x squared. F of 1 is just the y coordinate. So the y coordinate is just 1, or you can plug it in the function. 1 squared is also just 1. And now we just have to evaluate this function, or evaluate this limit, rather. So I'm going to leave this to you guys to go ahead and test this out. But after you run this through, you're going to factor the numerator, cancel common factors, and then apply direct substitution. We end up getting a value of 2. So you do that the same way we just did it in the previous example. So that gives us the derivative of the function evaluated at x equals 1, or the slope of the tangent line at x equals 1 is 2. So same thing, we get a value of 2. All we have to do to finish this off is just plug this in. Y minus y1 equals m times x minus x1. Let's go ahead and just solve this for y, just so we can, when we graph it in a second, we can see that it's definitely correct. So distribute the 2 on the right, add 1 on both sides, we get y equals 2x minus 1. So this is the equation for the tangent line for the function f of x equals x squared at x equals 1. So let's go ahead and graph this. Let's go ahead and graph f of x equals x squared. So I just plotted some points to try to make it look a little bit accurate. That's f of x equals x squared. And we wanted to find the equation of the tangent line at x equals 1. So here's x equals 1 right here. That's going to give us this point on the curve right here. So just by drawing in the tangent line, we can probably tell that the tangent line looks something like this, right? The direction touching the curve at the point, that's the direction of the curve. And if you look over here at the equation of the line, that definitely looks like the line y equals 2x minus 1. So even though it's probably not going to be perfect, it looks pretty good. So it looks like we probably did not mess anything up. Okay, so far, a quick little recap before we make this get a little bit trickier here. We talked about what a tangent line is, what a secant line is. We related why we use secant lines to find the slope of the tangent line using that limit definition, and we used f prime of a equals limit as x approaches a of f of x minus f of a over x minus a. We use that singular definition for basically every question so far, right? We also have this alternate definition of the derivative, which is arguably used more often going forward in calculus. So let's kind of derive what this formula represents, and I'll mention why this one is, I guess, used maybe it's a little bit more frequently than the other one. So we're going to start this off the same exact way here. Let's draw a function. And let's say we have this point right here. And if you want to call it r, you don't really have to call it anything. I just label it just so I can refer back to it, I guess. But let's say we have this point r. And let's say we want to figure out the slope of the tangent line at this point. And just so I can label this right now, we're going to label this an x value of a once again. So far, this is literally the same thing that we've already done, right? We have this random function curve drawn in here. We want to figure out what is the slope of this tangent line. You can even draw one in if you want. What is the slope of this tangent line at x equals a? And we're going to use, once again, probably pretty repetitive, we're going to use another point s that's going to move closer and closer to this point. So as of now, you should be saying, well, this is stupid because this is already what we did. But instead of thinking about this next x coordinate for s as just any x value, what we're actually going to do is we're not going to think about x getting closer to a. We're not going to be thinking about x approaching a. We're going to be thinking about this as a distance between these 2 points, and the distance is going to be approaching 0. So it's still literally the same kind of overall concept, where we're going to be moving this point closer to the point on the left, except we're not going to be thinking about it as x approaching a. We're going to be thinking about it as the distance approaching 0. So the distance, we're going to use this h to represent the distance between the two. So if this is a, and this is a distance of h, then the second point would just be called a plus h, right? This point plus some distance h away. So once again, though, we're still doing the same overall concept. We have the secant line, and we're going to be moving this point to this point, but what we're going to be doing is thinking about it as h approaching 0. So let's go ahead and take a look at the slope formula. So once again, we're still going to be using the slope formula. We know the slope formula is y2 minus y1 over x2 minus x1, and the x values we're using here, let's do the denominator first. The x values we're using are a plus h and a. So that's going to be a plus h minus a. So x2 minus x1, a plus h minus a. And then the y values are just going to be the function evaluated at each of those x values. So f of a plus h minus f of a. So the reason, even though this kind of looks like we're making this overly complicated again, the reason why this is going to be helpful is because the a's cancel off in the denominator. We're left with f of a plus h minus f of a all over just h, all over that distance that we're trying to have approach 0 between those 2 points. So this is something called the difference quotient. So just like before, when we move the secant line to where the tangent line is, the secant line is going to become the tangent line as h approaches 0. So that's where we introduce this limit notation, where this tells us the same exact thing as the other one. So we're still finding the same thing. We just have this alternate definition, which once again, we'll kind of see why we use this one more often going forward. And sometimes they tell us the same thing overall when we find f prime of a. So f prime of a is going to tell us the instantaneous rate of change at x equals a, or the instantaneous slope at x equals a, and it tells us the slope of the tangent line at x equals a. So what we do is use that quotient, that difference quotient up here that we just found a second ago, f of a plus h minus f of a all over h, and we're going to evaluate the limit as h approaches 0. So literally the same concept. We're just thinking about it a little bit differently. And this is just called the alternate definition of the derivative. So just so we don't have to go back and do the same types of questions that we already did with a different definition, one of the main reasons why this is going to be, we're going to use this definition we just went over more often than not, is because this is usually the better way to actually find the derivative function of our function f of x. So right now, so far we've been finding f prime of a or f prime of a number. Now we're going to be straight up finding the derivative function using this alternative definition, f prime of x. So going back to this previous page, what I'm going to do here, just so I don't have to redraw the whole thing, is let's go back to this page, but instead of thinking about this point as a fixed point a, because that represents a fixed number a, let's think about this as any variable, as any number, as a variable x. So if this is x, then that means this point would be x plus h. So we're just changing it to be from a specific value of a to any value using the variable x. And then if we take a look right here at this difference quotient, it becomes, or all of these a's are going to become an x. So y2 minus y1 over x2 minus x1, it's going to be x plus h minus x in the denominator, f of x plus h minus f of x. All of those a's just become the variable x. And the reason why this is going to be helpful is because we're going to use the same definition that we wrote below, except instead of a specific number a, we now have our definition of the derivative function, which allows us to find f prime of x, the actual derivative as a function with the variable x. So the derivative function f prime of x equals the limit as h approaches 0 of f of x plus h minus f of x all over h. So let's go ahead and run through some good examples now where we find the actual function. And this is kind of like the main chunk of this section in my opinion. So f of x equals x squared minus 3x. We want to find f prime of x. So after we find it, I'll mention why this one's going to be a little bit better. So f prime of x using this definition is the limit as h approaches 0 of f of x plus h minus f of x all over h. And the part where it gets a little bit tricky is the only two things we have to do. We have to plug in f of x, which is pretty easy, right? Plugging in f of x is going to be just minus whatever f of x is, minus x squared minus 3x. So that part's usually pretty simple. You just plug in the function. The hard part is going to be this part right here, f of x plus h. So f of x plus h, you might want to do this on the side. It's kind of up to you. I'm just going to plug it in at first right over here. But f of x plus h is just going to be substituting in x plus h everywhere you see an x. So instead of x squared, it's going to be x plus h squared. And then instead of minus 3x, it's minus 3 times x plus h. So right here on the left, let me highlight it. This part is f of x plus h. And then this part on the right is f of x. And then all we have to do here is simplify that numerator, which sure looks a little bit messy. We're going to simplify the numerator and then do direct substitution. Because remember, direct substitution is not going to work. We're going to get 0 over 0. What we want to do for this specific type is we want to be able to cancel this h in the denominator and then apply direct substitution. All right, so let's go ahead and simplify the numerator. And notice here that this is a polynomial, right? X squared minus 3x is a polynomial function. So simplifying this numerator is just going to come down to distributing and combining like terms every time it is a polynomial function. So we have a couple things to distribute at first. Let's go ahead and take a look at this part right here, x plus h squared. So if you distribute x plus h times x plus h or use the shortcut, you get x squared plus 2xh plus h squared. Then we can go ahead and distribute this negative 3 and distribute this negative into f of x at the end. So minus 3x minus 3h minus x squared plus 3x all over h. So once again, our main goal here was first substitute everything in and then do a whole bunch of distributing, which we just did. All of those parentheses are gone. Now we want to combine like terms. So anytime you have a polynomial function, f of x is going to completely cancel off. So these two terms on the right are going to completely cancel. Notice we have x squared minus x squared, negative 3x plus 3x. That'll happen every single time we have a polynomial function, which is why this ends up being not as bad as it originally looks. Notice now that every term left over in the numerator has an h. Every term in the numerator has an h as a factor. That means we can factor out an h as a GCF in the numerator. So we GCF factored out an h in the numerator. And now we get to the best part of the question, because h divided by h cancels to 1. So the h in the denominator cancels. Once that h in the denominator cancels, now we can apply direct substitution. So once the h in the denominator cancels, we apply direct substitution. Just make sure you're only plugging into h. You're not plugging into x, h only. So we end up getting, let me just plug it in, I guess, 2x plus 0 minus 3. So that gives us our derivative function, f prime of x equals 2x minus 3. So the reason why using this technique is usually a lot better than using the other technique that we went over is because this gives us the derivative function. So now when we want to evaluate the derivative at any x value, specific x value, all we have to do is use this function right here. So all we have to do now to evaluate f prime of 2 is plug it right in the derivative function, 2 times 2 minus 3. So we just find that f prime of 2 equals, 1. So once you find the derivative function, you don't need to ever keep on doing it over and over again for the same function. You can use that derivative function to find the derivative evaluated at any x value that you want. Okay, so once again here, I'll do a little recap at the end. But once we want the derivative function, automatically I recommend thinking about this alternate definition of the derivative. And if the function is a polynomial, you plug everything in, and then you simplify that numerator, distribute, combine like terms. Once you combine like terms, the original function on the right, the f of x will always cancel if it's a polynomial. So it cancels. Everything that's left over in the numerator will have an h. So you factor out GCF out in h, and then cancel those h's. Then you do direct substitution into the h's only, and that whatever's left over is your derivative function, and you can use that derivative function to find the derivative evaluated at any x value. So you don't have to do that process all over again. So for this last little chunk of notes here, we have thinking about the derivative as a rate of change. So remember, I've been saying this throughout every single question. When we get a value for the derivative, like f prime of 2 equals 4, you should think about that as the slope of the tangent line and the instantaneous rate of change of the function, or the instantaneous slope of the function. So we can take this one step further and think about this as one of our kind of basic physics problems when we think about position, velocity, and even acceleration. So let's say we have a function s of t. So usually in physics courses, you would see s of t is denoted as the position function. So s of t is going to be the number of feet, so it's the position, traveled by a car, where t is the independent variable seconds. So s is position in feet, t is time in seconds. And let's say we wanted to figure out what just s prime of 2 equals 20 represents. So s prime of 2 equals 20 tells us that after 2 seconds, the car is traveling at a velocity of 20 feet per second. So finding the derivative of position is actually going to tell us velocity. Because remember, think about the derivative as a slope. And if we think about the graph, to make it a little bit visually easier, let's say we have this graph where the x-axis is time in seconds, the y-axis is distance in feet. So this was just based on the variables. This is t, and then this is s for feet up here. If we calculated the slope, and we found that s prime of 2 equals 20, the slope of that tangent line is 20 at t equals 2. Always think about the units. When you calculate the units of slope, it's the change in y over the change in x. So that's going to be the y coordinates over the x coordinates. So that's going to be the units for y, which is feet, which is the units of x, which is seconds. So the slope would be feet per second, and that's why it gives you a velocity. Feet per second would be our units for velocity, which is the slope for this graph that we just created right here. So velocity, the velocity function will equal the derivative of the position function. The one kind of small thing to keep in mind is that velocity, for those of you in any physics classes, velocity isn't the same as speed. They're similar. Speed is a scalar quantity, velocity is a vector quantity. So what that means is that direction matters for velocity. So a positive velocity you would think of as moving forward, and a negative velocity you would think of as moving backwards. So we can go ahead and think about velocity as a derivative. Using that first definition that we used, we could also use the second definition that we used. That's where it kind of gets annoying, because we have our two different definitions for derivatives. Technically, they're both correct. Sometimes one of them will be easier than the other. So if we want velocity, velocity as a derivative is going to be s prime of a. So if we want to figure out the velocity of a particle or an object at time a, that's going to be, you can think of it as v of a, the velocity at time equals a, is the derivative s prime of a, which using that first definition from today, limit as t approaches a, s of t minus s of a over t minus a. So this is just the same exact thing as f prime of a equals limit as x approaches a, f of x minus f of a over x minus a. We're just using a different variable t and a different function s instead of f of x. So let's go ahead and answer one question using this concept. Hopefully it's not as bad as it seemed. So let's say we have a ball that's thrown straight up into the air. The ball is going to initially go up, and then it's going to, of course, fall down due to gravity. So we're going to say that when the ball is rising, that's a positive direction. When the ball is falling, that's going to be a negative direction. So a given formula just from physics for throwing a ball straight up into the air after t seconds is going to be this formula right here. This is ignoring air resistance for simplicity. So we have s of t equals negative 16t squared plus v naught t plus h naught. And let me just discuss what this represents. Once again, s, this represents the position or the height of the ball t seconds after you throw it. So you would plug in your value for t, and then also notice you also have two other variables in here. You have this v naught and h naught. This represents the initial velocity and the initial height from where you threw it from. So of course, this isn't something you have to memorize. We're just going to use it to answer these next questions. So suppose a ball is thrown straight up into the air. It has an initial height of 112 feet, initial velocity of 96 feet per second, and we want to go ahead and find the equation s of t after t seconds. So all we have to do is just straight up write this equation down and plug in the initial height and the initial velocity. So this is going to be s of t equals negative 16t squared plus the initial velocity is 96 feet per second times t plus the initial height, which is 112 feet. So all we did was substitute in our given values into v and h for the initial velocity and the initial height. Okay, so let's use this equation. Now all we have to do is take a look at this equation and nothing else. Part B, we want to know how high above the ground is the ball at 5 seconds. So all we have to do for this one is evaluate s of 5, right? We're looking for height. So we want to know how high, that's s of 5, the height, after 5 seconds. So there's no calculus involved here. We just have to use our function and plug in 5. So plug in 5, evaluate this, plug it in the calculator, and we end up getting s of 5 is 192 feet. So let me just circle these because we're going to need them in 1 second here. Now for the calculus portion, hopefully that those first two weren't that bad. Now for the calculus portion. What is the velocity of the ball at 5 seconds? So of course, we do not have the velocity function. We have the position function. So what we have to do is use the fact that we can actually find the velocity function. And this is where we technically have two options. I'm going to use this form of the equation that was written right above here. Technically speaking, you could use the alternate definition if you want also, and then plug in t equals 5. I'll leave that up to you if you want to try that. So what I'm going to do here is use that definition that was written above. The velocity, which I'm just going to write v of a for now, just to write the original general equation here. The velocity at time a equals the derivative of position at time a, which is the limit as t approaches a of s of t minus s of a all over t minus a. So once again, don't let the variables confuse you. This is literally just the same first function formula that we used at the start of today. Now let's go ahead and plug in what we're actually looking for. We want to find s prime, you can write it as v of 5 too, I guess. V of 5, which is s prime of 5, and plug in 5 into all of these a's. So that's going to be limit as t approaches 5 of s of t minus s of 5 over t minus 5. And now before we actually evaluate this, we just need to plug in two more things. We need to plug in s of t and s of 5. So let's just write what we already have before we do that. Limit as t approaches 5. Denominator is just t minus 5. So let's look at s of t. S of t is right up here. S of t is the function itself. So we can go ahead and plug that in. Negative 16t squared plus 96t plus 112. Right? So all of that, what I just wrote, was just s of t. And then minus s of 5. We already found s of 5 a second ago. S of 5 was 192. So this just represents s of t minus s of 5. So now we can simplify one more thing. It looks like we can simplify those last two constant numbers in the numerator. 112 minus 192. And we get minus 80 when we combine those. So we did all that work. Hopefully it wasn't too much. We just used this definition, plugged in our a, which was 5, into everything, found s of t, which was the original function, evaluated s of 5, which was 192, simplified, and now all we have to do is evaluate this limit. And this is a rational function. So of course, when we try direct substitution, it's not going to work. We're going to get 0 over 0. So we should be thinking that we will end up getting, we will end up being able to solve this by factoring. It looks like we do also have a GCF of 16 in the numerator. I'm going to factor out a negative 16. If we factor out a negative 16 in the numerator, we're left with t squared minus 6t plus 5. All over t minus 5. And now it probably looks like it cleaned up kind of nicely. because this quadratic expression left over, we can factor that one more time. Two numbers that multiply to 5 that add to -6. T minus 5 times t minus 1 all over t minus 5, which is perfect because in order for this to work, we had to actually be able to cancel off a t minus 5, which we do. So we're just left with limit as t approaches 5 of -16 times t minus 1. Now we can apply that direct substitution. And since we're applying the direct substitution, now we don't need the limit notation anymore. -16 times 5 minus 1. So we end up getting -16 times 4. So -64. So even though this is the answer, we should just kind of consider what this represents. We just found that s prime of 5 equals -64. And this was the velocity, which was in feet per second. So s prime of 5 equals -64 feet per second. So what this represents is 5 seconds after you throw the ball straight up in the air, the ball is coming down at 64 feet per second. We know it's on the way back down because the velocity is negative. All right, so a little recap of this section. We basically went over, even though we had a lot to kind of cover, tangent line, secant line, and everything, and the derivation of these little formulas. We talked about the introduction to what a derivative is. We talked about these two separate formulas, where the first one was, let me scroll back up. This first limit definition of the derivative, which tells us f prime of a equals limit as x approaches a, f of x minus f of a over x minus a. It tells us the slope of the tangent line at x equals a, or the instantaneous rate of change at x equals a. And then we also talked about the alternative definition, which we originally discussed this alternative definition, f prime of a, which tells us the same thing, limit as h approaches 0, f of a plus h minus f of a over h. But the main reason, in my opinion, why that's the most helpful definition is because we more prominently use this definition to find the derivative function of our original function. So we replace those a's with an x, and we can find the derivative function using this definition. So technically, most of the time, both of these definitions work. One of them might be more easy than the other one. In my also opinion, this is kind of the big one for the day. All right, so that is it for this section.